今スタートします。
So do I share or not just yet?
Not yet.
Not yet.
Not yet. Okay, perfect. Yeah.
Yes, the live event just started.
Okay, welcome to International Keynote lecture session now. Hope everybody enjoyed the academic discussion during the day. It's our great pleasure to open this keynote lecture at the last event before the workshop. My name is Yuji Nakamura from Toyohashi UTech, chairing of this session. This time, it's our honor to invite Professor Guillermo Rein from Imperial College London as a speaker of this evening keynote lecture. Although everybody knows him as a leading scientist in this community, but let me briefly introduce and touch his achievement quickly. Professor Guillermo Rein currently belongs to the ME department of Imperial College London and is known as a most reputed researcher in the fire science and environmental science. Professor Rein graduated his bachelor degree in Madrid, in Spain, then received a master and a PhD degree from UC Berkeley, year 2005, under the supervision of Professor Carlos Fernandez Fellow. In the year 2006, he started his professional career at the University of Edinburgh and worked there till 2015 as a senior lecturer. And on 2015, Professor Rein appointed at the Imperial College London to leading the science thermal energy group first. Since 2017, he's offered a professor position in fire science. His achievement summarized 8 books and over 100 journals and many awards, including the 2 times Distinguished Paper Award from Combustion Symposium and a Fellow of the Combustion Institute and others. Such an important person is generally very busy. Nevertheless, Professor Rein kindly accepted this offer to share us his recent work from London, which is the 8-hour difference. Sorry about that. We heartily appreciate his kindness. His talk is entitled Wildfires, Tall Timber and Battery Fires, Combustion Science at a Crossroads with Climate Change and Safety, which is a very, very interesting topic. Now, let us welcome Professor Guillermo Rein. Guillermo, now mic is yours, and please start your presentation whenever you are ready. Your mic is not on. Okay, thank you.
Can you hear me well?
Yes.
Perfect. Thank you. Thank you very much.
Could you sharing your Windows?
Yeah.
All
I
right.
will do that just now.
Excellent.
Perfect. Yeah, thank you very much. Let me start saying that it is an honor for me to be presenting. So thank you so much. The time difference is not a problem at all, and above all is the joy of being addressing this very prestigious and expert audience. And I just wish I was with you there in Japan. For the time being, I will have to delay my visit to Japan, but I look forward to be happening soon. Can you see my screen? Excellent.
Yes.
So for the next, thank you, and it is an honor for the invitation. So I just want to spend a few minutes talking to you about things that we all know about in combustion and things that we are seeing that are changing in society, and how we can all align ourselves into that context. So I'm going to be talking about Crossroads in general, and then I'll be talking about climate change and fire safety. In the first topic, I will talk about fire research, which some of you are very familiar with, and I'll be talking about wildfires and tall timber. These are buildings that are very tall and they're made of timber. And then I'll be finishing talking about battery fires. So we are all scientists, so we are all familiar with the process of the scientific discovery, where we are studying topics and we are discovering new things, and we go through beautiful places. Sometimes are beautiful, sometimes are not that beautiful, but in general, the success story that we tell in science is a succession of great discoveries, and we take different paths, and we go with different people and different collaborators and different schools of thought. We also create wonderful things in this process of following this path of discovery. this path, because there are several paths in the discovery. We create bridges between different disciplines and different schools of thoughts, and we just enable the continuous discovery of things. And in this process of going through roads and building wonders, we obviously find plenty of opportunities to take different paths. This is what happens in a crossroad. I might simplify today the topic, but in reality, we are constantly exposed to crossroads, and we are constantly, as scientists, taking different turns and different directions and putting our resources in different paths. There is a crossroad that is quite important in the modern times. Is related to the turn of the century, in the 21st century. The topics that our societies around the world, and that our authorities, and that even our families consider to be the most important, have changed. And I think that if we were to be asking this question around, and we can see this in the media, and we can see this in people in the street, the top concerns that people are talking about are climate change and the topics that climate change is bringing to the forefront. And sustainability is a big important thing that we've been trying to achieve and to maximize for a long time. And also energy systems, the ability to provide energy so civilization can continue forward and do these things. So taking into account these three topics, we realize that combustion has been already, as a scientific discipline, contributing to these three topics for a very long time. Combustion science is, and I know I agree, I shared this with many of you today, it is one of the most fundamental branches of science. It has led to great discoveries, and more discoveries are coming in the future. But maybe combustion in the past has found its relevance more in power generation and propulsion, namely combustion engines. Also, of course, the Combustion Institute recognized 14 colloquia, and the topics that are covered at the Combustion Institute are very broad. But if you investigate why is combustion still relevant to society, it is mostly in the past because of combustion energy and propulsion. And this is changing because of the topics that I'm presenting today. Their emphasis is changing. Climate change, sustainability, and energy systems is making all scientists all around, not just combustion, all scientists, to rethink the path they want to take when they go forward in this constant finding of crossroads that I mentioned before. So the question is, what can the combustion community do when they find themselves in the crossroads that we are with climate change, sustainability, and energy systems? In this particular crossroads, I would like to call your attention to a crossroad that you are familiar with already, and that I've been working on as well on a long time, together with other colleagues, many of them in Japan, like Professor Nakamura. It is the specific topic of safety. If in this pyramid over here, we see what is called Maslow's hierarchy of needs. Is a specific interpretation of human needs, and it shows at the bottom our basic needs, our needs for eating, for drinking, and to sleep. And building upon needs, we end up in the pinnacle of the pyramid, which is self-realization and the true endeavor of humanity. The second layer at the bottom, after being able to eat and to being able to drink and to sleep, it is actually safety. We need to feel safe in order to continue in our progress to social esteem and self-realization. And so we cannot, I cannot emphasize more the importance of all safety for society. Among all those that are related to safety, there are 2 or 3 that are part of the Combustion Institute, namely fire safety, fire and explosions, and even toxicity of the products of combustion are topics related to safety. So this is related to the study of flammable substances and how they develop when they actually undergo combustion, which is mostly unwanted combustion. It is not the combustion that we do on purpose that is studied in other devices. This is the unwanted combustion that has happened and threatens the safety of people, their property, and the environment. So I am going to be talking about that specific path of combustion science today, just to emphasize again, of the 14 colloquia of the Combustion Institute, one of them is fire research. It's called fire research. It's the study of fire, and it is a branch that I'm going to try to convince you in this plenary today that is a branch that is gaining extra relevance and is emerging as an important topic related to climate change, sustainability, and energy systems. So if we have, I'm going to do the intersection between three topics. Obviously, we are all combustion experts, so the circle and the entity of combustion science is going to be there. And then when we intersect that with the safety of people, property, and the environment, then we end up in the subset that is highlighted in a different color of fire research. And then when we intersect that with the modern views of society about the importance of climate change and sustainability and energy systems, then we end up with this point at the center. That point at the center is the one that I want to discuss today. You can imagine already that the intersection of combustion and climate change has different topics that I'm not going to be talking about today. And these are very exciting topics, but maybe not all of us were familiar with the ones between climate change, fire, and combustion. So I'm just going to be choosing three topics today. I recognize that there are way more than three topics in this intersection of these three ideas. I'm just going to be talking about wildfires, tall timber buildings, and lithium-ion batteries as three examples. I will not go too much. I will not go into the details of the science. I will be treating this lightly. I will be trying to call your attention to the overall objective and the overall problem that we are facing. And hopefully by the end of the plenary today, I would have convinced many of you, some of you, maybe many of you, to start looking into this and to join forces in order to help society in these modern ideas. This is just the tip of the iceberg. There are many other topics, and I can happily direct you into the other topics that are happening in the literature. So the first topic number one, is wildfires. Wildfires is the specific intersection between combustion, safety, and the climate. There are also obviously relationships with sustainability and energy systems, but the most important intersection here is the climate change. In combustion, we are going through a phase where most people in society might consider combustion technologies to be the cause of climate change. Obviously, that's not true, and that will be a simplification of the situation. But many people consider combustion technology in that category. It is interesting because combustion was not invented by humans. It was discovered by humans. Nature invented combustion, and nature had a very important role for combustion. In fact, without combustion, namely wildfires, there would not be life on Earth. There would not be ecosystems, which most ecosystem has been shaped by the presence of wildfires over thousands of years. There would not be a closed loop for the regulation of oxygen. You know, oxygen, the 21% in volume that we have in the atmosphere. Well, fire is one of the most important mechanisms to make sure that that value remains at 21 and it doesn't go higher. The carbon cycle, before we humans start to alter it, it was closed by wildfire. And even climate, one of the regulators of climate, it is actually over the long term wildfire. So it is interesting that at the planetary scale, which is a very important scale, combustion is absolutely essential to life. Yet you will not see much of a combustion experts looking into this topic. This topic, unfortunately, is not well populated by combustion experts. And I have this call for you today that there is no good reason for this. And I think many of us should be paying more attention to the natural process of combustion that is so important to humanity. Just to give you an idea, obviously you know this, but I'm just providing the overview. that fire is everywhere on the planet. This is a combined satellite image of the year 2010. I just chose that year for no specific reason, just because it was easy to find. Of all the fires that have been able to be seen by the satellite. Satellites all around the world, there are many of them, can only see the big wildfires. They cannot see the small ones. So this image that you see over there, when you see red is the presence of wildfires, yellow is a particularly strong presence of wildfires, and the brown of the green means that there was no big wildfire in that location in that year. You can see that most continents, except Antarctica, are actually active in wildfires, that Sub-Saharan Africa and South America were particularly busy that year. You can see also the Mediterranean, you can see also United States, you can see Siberia, you can see Australia. These are the ones that are in the news very often when there are big wildfires and people are concerned about this. So the planet where we live, it is a planet where fire is present every single year, even before we humans became a species, and it will continue happening for many, many thousands of years. So embracing these phenomena, understanding these phenomena, and using it for the good and to protect against the bad fires is a very important role for scientists. When wildfire goes wrong, as it is happening, for example, in California in the last few years, it starts to threaten people's life, property, and ecosystems, and that's quite painful to be part of. This is every year around the world, not just in California or in Canada on the Mediterranean, all around the year, we're talking about thousands, if not millions, of refugees, fire refugees, I call them, that have to leave their homes because an impeding large wildfire is arriving. And when they go back, sometimes they find that they don't have a home anymore. Some of them are very lucky. The majority, when they go back, their home is there. The community has been affected, but sometimes when they come back, there is no home. Thank you. The bad fires. We also have the straight link to the climate. Climate has greatly affected and increased the bad fires. So climate as a whole is not bringing more fires. We actually have about the same number of fires. When we say number, we're referring to small wildfires or very large wildfires. The small wildfires could be considered good fires because they're actually helping the ecosystem to be renewed. The big fires, the big wildfires, some of them are called mega fires. Those are very scary, and those are bad fires. They're actually damaging the ecosystem. They're destroying it in excess, and they actually put lives at risk. So what we see that climate is bringing more of the bad fires. This data over here is coming from the United States. In blue, over the years, over the last, since 1985 to 2015, in blue you see approximately the number of fires that we are seeing, which remains relatively constant in the United States. But if you see the size of the area that has burned, which if you divide by the number of fires, giving you the average size of a fire, you can see that it's clearly going up. There are many reasons for this. It's not just climate change, but climate change is one of them. The other two is that people are coming in and out of the rural areas, of the wildland areas, and their presence or lack of presence is altering fire behavior. And the third change is that people are changing the use that they have of the land, from making it agricultural or abandoning agricultural lands. Also in the United States, they have the specific problem that over the last 100 years, they've been suppressing every single fire, the good fires and the bad fires, wildfires, and that has led to a buildup of fuel. And it means that is making the next fires, combined with climate change, even larger. Another very concerning signal that we see in the topic of wildfires is related to the overwhelming presence in the recent years of fires in the Arctic. So the Arctic has forests, it has beautiful ecosystems they're pristine. There are not many people living in the Arctic. And we're talking about the Arctic, especially in the north of Russia, in Siberia, and the north of Canada, and even of Alaska. And people knew of wildfires happening in these forests in the Arctic. And also when the forest, the boreal forest disappears, the landscape in the Arctic is still flammable. It has wraps and it has a soil that is rich in carbon matter that can actually burn. And we knew of wildfires in the Arctic, but they were very rare and it was very difficult to observe them. And in the last few years, they're not rare at all, and they're actually quite easy to observe. And we are seeing an unprecedented number of wildfires in the Arctic. When we go into the Arctic, of the three changes that I mentioned before, climate, people, and land use, there is no people in the Arctic. So we cannot really claim that is their presence that is actually creating more fires. Even the explorers or the people who might be doing some industrial activities, they actually are not significant. It is not also the change, neither the change of land use, because no one is changing the Arctic lands from being agricultural to something else. So what will happen is that we see in the Arctic is clearly a climate science signal. Obviously, we want to understand wildfires in order to do all the good things that they can do for the planet, but also we want to understand wildfires to stop doing the bad things that they can do, in particular to put people, property, and the ecosystem in danger. So fire, obviously, it's a combustion process, it's unwanted, and it's uncontrolled, and it's happening in the open. It is burning fuels, which are very heterogeneous and complex, biomass, they're talking about leaves and needles and branches, and even the trunk, and even the soil itself can burn. So we talk about very different types of fire that happen in natural environments. The flame that will appear is a diffusion flame, and it's very turbulent, especially the bad fires, which have very large, very tall flames. That is very turbulent. There is an incredible amount of radiation. There is a presence for convection, especially when the wind is blowing and is moving the flames in a specific direction. And there is going to be flame contact between the flame and the different fuels. And all these together is the process of combustion, and the fire will move forward, releasing some products of combustion. Just to call attention that it's not just the wind, but also the slope. The slope of the place of the forest that is burning has a significant effect on the dynamics, just because of the presence of gravity and the inclination of the or the lack of inclination, or the relative inclination, sorry, between the flame and the fuel means that upslope there is less distance between the flame and the fuel, and that means that there is a higher heat flux from the flame to the fuel, and it means that the spread rate is higher with the inclination, obviously being the maximum when it's maximum spread when it's perpendicular going upwards. And when it is going downwards, when the slope is negative, the distance between the flame and the fuel is larger. So by radiation convection, the transfer of heat is weaker, and actually fires go slower than the slope, and they go up the slope. So wind matters, fuel matters, and gravity matters. Slope matters. And we don't have, just to call your attention in our understanding of wildfires, we don't have a good theory at all to understand the spread of wildfires. The community is in trouble because we remain using a fascinating theory of flame spread that was developed by Dr. Rothemel. That's a photo of him. He came up with a relatively simple but powerful relationship that said the rate of spread, R, which is also S, is the ratio of the amount of energy that is released by the fire divided by the energy that it requires to heat up to that point. There are different terms regarding to the moisture of the fuel, which is very important, regarding to the wind and the slope. These are terms that that accelerate the spread rate with wind and slope. And then we have the density of the fuel and how effective is the heating of the fuel and what is the heat that it requires to ignite. It will be the heat of pyrolysis or the heat sink to ignition. This theory that has about 50 years of age remains the best spread model that we have for wildfires. And the reason is that we have not been able as a community to find something better. This will be equivalent in combustion science in the study of flames to maybe to Malar-Ernst Atelier theory of the 1885. This will be the equivalent. So just to give you an idea, in the understanding of wildfires, we are lacking the type of knowledge that society is requesting from us. We don't have good theories of flame spread. We don't have a good understanding of why wildfires propagate at a specific direction at a specific rate. And that is a challenge that combustion scientists are needed. Because if we combustion experts, the people who truly understand combustion processes and are able to do experiments and modeling, if we are not present in this topic, someone else will do. And if someone else does it, they are not going to bring combustion science into it. And that will be a major loss for the combustion community, where a very important combustion topic is not being addressed by the community where the topic belongs to. So I am putting forward here an official call for more of us, more combustion scientists, to be present in the study of wildfires. We have a precedent for this, the complexity that we remain in the topic, despite its massive importance, planetary importance, importance to people, so many people around the world, except in one continent, in Antarctica, where there are not many people, everybody is exposed to wildfires. Already Professor Hotel, one of the founding fathers of the Combustion Institute and of our topic, he said that a case can be made for fire being next to life processes the most complex of phenomena to understand. This is important because life, not just the human body or life in the planet, it is indeed a very, very complex process. And we're talking about thousands and thousands of doctors and physiologists and biologists and zoologists studying life in the planet and life in the human body. But we're not that many scientists doing fire and doing combustion. We maybe are about 5,000 combustion scientists in the world. So we have an equally complex problem to study, fascinating and complex as people studying life, but we are outnumbered. So which means that there is a space and a need for more of us to study the topic. Some of you that are familiar with fire research, and maybe some of you have been studying wildfires, then you would have your idea of how to do this, and I encourage you to continue it. Just if some of you are thinking of, but I am an expert in, for example, doing combustion experiments, or I'm an expert in computational models, how can I combine this? Well, one specific approach my group follows it is that wildfires that matter are at the field scale. We're talking about kilometers scale, so it's a very large domain. And we combustion experts are more used to much smaller domains, but that's okay. The question is how can we combine laboratory studies and modeling studies such that we can be in the field. So the idea is we develop the fundamental mechanisms that are at play in the field. We develop and isolate them in the lab, and we conduct experiments that are high fidelity, controlling those mechanisms. And we develop high fidelity models, and then these models are able to replicate and to predict accurately the high fidelity experiments, and then we can launch the models to go into the field. It would not just be one model, it will have to be multi-physics because there are many different processes that are combined in this field. And this approach of having well-posed laboratory experiments that are upscale into the field through high fidelity models is the way combustion scientists have been operating for a very long time for specific different problems. So this is a methodology that can be used also to study wildfires. We should not be afraid that because a wildfire is a very large phenomena, that then we cannot study in the lab. For example, my group at Imperial College, as we speak, this is what we do. We do experiments in the lab, that we stop to think about the mechanisms that we want to study, and then we launch this into the model with numerical models. We also do field studies. So we go into the field and we study this, which typically combustion scientists have not done, but that's absolutely fine. That could be something that can be learned as an addition to some experts of combustion that want to be involved in wildfires, the field studies. That was topic 1, wildfires. Now I want to mention topic 2. Topic 2 is related to sustainability. So sustainability and fire. And the specific example that I want to highlight is timber. So we humans have been building houses out of timber for a really, really long time. Probably timber was the material that we use the first as a species to create tools and to create homes, probably even before stone. But I'm not talking about, and I realize that in Canada, in Scandinavia, and even in Japan, timber or wood has been used as a construction material for a very long time. But I'm not referring to the traditional structures of wood. I'm referring to the future structures of wood that are arriving, in particular tall timber. We're talking about skyscrapers, very, very large buildings, in particular tall buildings that might be arriving to cities very soon, made of timber. The breakthrough is because this is not just normal timber. This is what is called engineered timber. In particular, CLT, cross-laminated timber, or GULAM, which stays as glue and laminated wood. These are different types of creating strong structures that are made of timber, and they are so strong and so light and so inexpensive that there are already dozens and hundreds of architects around the world dreaming and proposing and drawing and designing high-rise buildings, skyscrapers made of timber. And just giving you examples of London having obviously one. You can see there, this tall building is made of timber. It's not built yet. It's not even approved, but people want to build that in London. This is St. Paul's, and this is the Millennium Bridge in London. This is the Thames, close to us. So architects wants to do this in Chicago, in Tokyo, all over Europe, even in South America and in Asia. This is not just a few examples. This is considered to be the future material of cities. The reason for this is not just that it's pretty, which it is very pretty. Humans really like wood. It's not just that it's inexpensive and it's light and it's strong. It's because wood itself captures carbon. So the building itself can become carbon negative. And this is very important, particularly because steel and concrete, which are the main materials that we use for construction of large buildings, are not carbon negative. They are actually very intensively carbon positive. So in the modern ethos that we see of climate change and carbon emissions and sustainability, making buildings out of wood becomes extremely attractive to very large sections of society, authorities, and architects and engineers. The question is, why is this not happening? And there are several reasons why this is not just happening. There are several reasons why these buildings have not been approved just yet to be built, especially the very tall ones. And I can tell you that the first reason people don't want to discuss too often, because all the people outside this room, they don't understand, is fire. There is a concern with the fire response of a tall building made of timber. Obviously, timber is flammable. It's just a matter of altering the degree of flammability of the timber. It can be very flammable or lightly flammable. It is flammable. It means that the wood itself starts to burn. And if it's a structural element, and we're talking about structures made of timber, tall structures, so they have to carry a significant load by gravity and wind. If they're burning, they start to lose section. They become smaller, right? This is an analysis here where we have the original depth of the wood. This is time. There is an amount of heat flux coming from the top. And then what happens is that immediately first the wood starts to dry. Then it actually starts to pyrolyze and it leaves behind a char. And then this char can actually burn together with the pyrolysate, and it leaves an ash of layer. And after some time, minutes or hours, what we end up is we have lost a section of the wood, and only this section remains. And it means that the structure of the sky-rise building is not as strong as it was, and it could actually lead to collapse of the high-rise. High-rise buildings take longer time to evacuate. And then there is a question of how do engineers can prove the authorities that the skyscraper made of wood is as safe as a skyscraper made of steel and concrete. And this can be done. At least I believe, and many of us believe, that this can be done, but we don't know how to do it just yet. And there is a significant amount of research as we speak, trying to help engineers quantify the safety of a skyscraper made of wood. And I can tell you that this research, about 80% of this research, it is in the realm of combustion science. And the experts that are doing these studies are using the concepts that are very familiar to combustion experts. So we're going to be talking about wood. The idea is that in order for an engineer to design the structure made of wood, they will have to come out with, just very quickly, I'll tell you what is the process. The engineer and the authorities will have to say what is going to be the fire that is threatening the structure. They will have to agree. There are many different options they can do. They can use computer models, or they can use curves that are already set and parameterized. Then they expose these curves to their timber, and they come up with what are called the charring rates, because charring rate is the rate at which the structure is losing section. It is absolutely essential to know, is this rate high or low? Because if the rate is low, that means that the structure is losing section very slowly and is much safer. And if the rate of charring is very high, is very fast, that means that the structure is being lost quickly, and that is more concerning. In order to calculate the charring rate, we need to do heat transfer, we need to understand the fire, but we also need to understand the pyrolysis process. Pyrolysis in the presence of heat transfer for a material that is flammable like wood has always been and will always remain in the realm of combustion science. And then the engineers will take those charring rates and then they end up to a structural calculation. So if this tool over here is not present, if we don't understand the process of pyrolysis of wood involved in a fire, we would not be able to provide engineers their ability to calculate the structure. So as the wood is heating up, as I said before, there is degradation of the material properties, the wood becomes weaker and the char is actually brittle and doesn't carry strength. There will be ignition, there will be a fire that will be spreading over the surface of the wood, and then that will lead to a section loss. If we reduce the equations, which in reality there are hundreds of equations, you know this, that is involved in the process of wood burning, just think of not just small particles of biomass burning in a furnace for power generation when we are burning biomass. Or think, for example, of when we are doing a bonfire in a chimney in our homes and we are putting logs there to burn. Well, these are the multiple processes that are involved. Obviously, there is heat transfer, there is mass transfer, there is momentum transfer, and there are chemical kinetics. If we reduce this process to the two smallest reactions, the small set of equations that we can think of, we will end up with conservation of species for the chemistry, and we will end up with conservation of heat for the transfer of heat inside the solid. These are the two most important equations. We can add to this and create complexity, but these are the two of them. When we have this and we can solve them, we are able to predict what is going to be the position of the char in our sample as a function of time. And this is just an example that we've done in my group, for example, where the line in red is a prediction with a computer model of combustion science related to pyrolysis in wood, of a thick sample of wood. And the dots in red are experiments that were found in the literature. And you can see for different scenarios, different types of fires, and how the model is able to predict accurately the evolution of that char that is being formed, which is absolutely essential to allow then engineers to make calculations. Obviously, this is far from over, and I will predict that there's at least 10 to 20 more years of research on the topic before cities which are carbon negative by the mass use of timber can happen. So I call for your attention to help us understand the burning of wood. And I want to link this to something important. Burning of wood. Wood has not been the most popular material in combustion science. We prefer simpler fuels and in the gas phase, but wood is in the solid phase and it's natural. So it's not synthetic. And it's not just that, is the material that nature has been burning for thousands and thousands of years before we became a species. As I said before, nature invented fire. We just discovered it. And nature was burning wood. And then we became a species, and there was this a revolutionary moment in our development as a species and as civilization when we started to burn ourselves and control fire. When that happened, we were burning wood. So we can say that wood is the most important fuel for the planet and historically the most important fuel for humanity. And yet is one of the fuels that we know the least how it burns, mostly because of its complexity. So this is a great challenge to the combustion community, really smart, intelligent people with ability to do experiments and computer models, and they're not afraid about complexity to take part of their attention into this crossroad and help us understand how wood truly burns. The process of burning wood is, as I said before, is very complex. It's not just about heat transfer and chemical kinetics. We have multiple physical and chemical processes, and just want to highlight some of them here. In order, the combination of all of them will give us a response of the temperature as a function of time on the surface. And this could be a biomass that is normal, and this in green could be a biomass where we actively have reduced its flammability. If we reduce its flammability, it means it will heat up less. And also when it reaches the critical points of ignition, it would be later, and immediately would mean that the charring rate and the rate of degradation of the material has been decreased. So you can see already the processes that we are dealing with. We have the smoldering, whether it's combustion without a flame. It's not just about flame. We have the charring, we have the pyrolysis composition, we have radiation in depth, conduction and convection couple. We can have wood is actually a porous material, so we have porosity, and we have multiple properties are changing in temperature. The complexity is serious. And now I'm going to the third topic of today. Is related to energy systems and sustainability and climate change and fire, and is actually batteries. Batteries, in particular lithium-ion batteries, is this revolutionary technology. It's essential technology. It's everywhere. Right now, as I speak to you, I'm using 2 of them, and I'm sure there in the room where you are, you also have several hundreds of them. And it's in our cars, it's in our airplanes, it's in our transport means, is consumer electronics. It's also used in the grid to provide stability. It is absolutely everywhere. And it's very good technology. It has a problem. One of them is that it's a hazard. It is a hazard. Batteries are not just that they are made of flammable materials. In a battery, about more than 2/3 of the materials are flammable by themselves. So you can actually take them apart, put it into a combustion chamber, and they will release heat. It's not just that they're flammable. We are surrounded by flammable materials in our lives, polymers and nature and biomass. It is not only that when it burns, it produces a high level of toxicity. The materials that are involved, the metals and the oxides that are involved in batteries, release very toxic materials, seriously toxic, much more toxic and potent than typical combustion processes of burning wood on polymers. And if that would not be enough, that are flammable and toxic when they burn, they also provide an ignition source of their own. They actually self-ignite. So you don't have, unfortunately, to wait for an arsonist or for an accident in a nearby element. They themselves, the batteries, can undergo ignition. So this triple hazard and the fact that the hazard behaves in a different way to other fires becomes an issue. Statistically, it is rare for a battery to ignite. But because there are millions of batteries all around the world, it means that we are seeing battery fires and that we need to be addressed. And they are being addressed, but slowly. This is just a table where you can see some of the major fires that we have seen with batteries. We stopped collecting this table in 2019. Since then, there have been other ones, but you can see there are massive issues with cell phones, with computers, with electric vehicles. In aerospace, there was a big issue with Boeing, hoverboards, because this is a new technology that actually can have, or scooters can have a battery, in marine, and even in the use of batteries for stability of the grid. And these are the big ones. These are the ones that made the headlines. Some of them led to the loss of life, but mostly they led to economic losses and concerns in the sense of the loss of credibility for the technology to really provide everything they need to provide. I'm happy to say at least that upon each of these big fires, the industry that develops batteries has put more attention into the fire hazard of the batteries. But in 2010, for example, there was very little research by these companies in fire safety and fire behavior, very, very little. Now, in the year 2021, I can tell you that most of these companies will have at least one or a small group of fire experts looking into this. I can go into the future and see that their fire expert team, which definitely should be combustion experts, and they need to be combustion experts, they would be much bigger. So I encourage you to help into this topic, which is not going to go away. Batteries, reactive batteries with flammability, toxicity, and self-ignition capabilities. a long
Guillermo,
time.
you have 5 minutes left.
Perfect. Thank you so much, because I'm just finishing. The complexity of understanding the flammability and the fire behavior of batteries is multi-scale by nature, just by the way actually scientists understand batteries. So we have the materials, we have the structure, we have the cell components, we have the cell itself, we have the module, and then we have the pack. And the fascinating thing is that the fire behavior of each of them is different. Obviously, at the microstructure, at the active material scale, we're looking into the chemistry itself, in the same way as we do in combustion, just chemistry without heat transfer or anything else, without fluid mechanics. And then when we start to build it up, we start to bring the heat transfer and the thermofluids and the complexity of the domain. So just when we try to understand the fires in batteries, we recognize that there are multiple ways by which they can ignite. These in the community are called abuse conditions because no one wants them to ignite. Therefore, they recognize that the conditions that led to ignition are an abuse of the battery. They don't recognize that that is meant to happen, right? They could be electrical abuse, short circuit, namely. They could be mechanical abuse because they have been penetrated, for example, they have gone through a shock or an impact or penetration of a body. Or it could be thermal abuse because they are in hot conditions. It could also be that they're defective and they develop themselves faults inside. Itself could be say that that's an electrical abuse condition, but it's because it's caused by a defect. It's internal abuse use. It's a different case. And then one topic that particularly important for combustion scientists, I would say, and my group has been involved, is self-heating ignition, which is the battery by itself. It's not connected. No one has mistreated it. It's not in a warm environment. It just by itself, while it's being stored for long enough, it suddenly catches fire and then it develops into a. It's just as it was with Frank Kamenetsky and with Semenov theory and all the ignitions theories that we have in the combustion community is a balance between heat generation and heat dissipation. And when the heat generation is faster, then because it's exponential thanks to our Arrhenius type of reactions, this will end up in the ignition and the process. And then once you have ignition, this is an example of what you will see in temperatures as a function of time. When you put a battery in a hot environment, for example, you see in red how the temperature of the battery is rising. In black is the temperature of the oven, for example. This was a hot oven, obviously. And there is a point where the battery reaches the temperature of the oven and it goes above it. So this was actually kind of what is called thermal abuse kind of approach. And we can see all the stages that the battery is undergoing. But also when one cell is igniting, cells that are next to each other, as it happens in the pack, then actually the ignition of one of the cells might lead to the ignition of the near one, and that's what is called the process of propagation. This happens, and this will continue happening, and there is a call for scientists to help us understand this process, so actually solutions for safety. Just to give you an idea, when we think of the chemistry involved in batteries, it is a chemistry that is way more complex than the chemistry that we have in normal hydrocarbons. In normal hydrocarbons, we recognize the presence of hundreds and even thousands of reactions. Well, the state of the art of the chemistry involved in a fire of a battery right now, as we speak, it is just made of these 5 equations. So 5 chemistry steps is very little compared to the amount of knowledge that is required or the knowledge that actually combustion scientists are able to provide. This is a call for example, the expert in chemistry among you to go into this field because there is a need for combustion scientists to understand these fires. This is just an overview. I will not spend time of what the literature in battery fires is saying. And what it's saying is that we know something about the ignition of batteries in a cell, but we know very little about propagation or smoke toxicity, and we know very little about what is happening at the large scale domains. We know more about what is happening at the small cell domain. So this, I'm finishing. I just want to present this overall dream that I have is that I have a dream for combustion scientists and for me to combine physics fundamentals with chemistry fundamentals, starting at the small scale and building it up until little by little the 2 of them are combined. That would be called the topic of combustion properly, when physics meets chemistry, and then go up the scale until we are able to address the typical real threat to the community, which is fire, based on the fundamental physics and fundamental chemistry. Just I've talking about climate change, sustainability, and energy system. I've talked about the massive importance of bringing combustion science into this. This will make our field as relevant as it has always been, but it will require a change in focus. And this is just the tip of the iceberg. Wildfires, timber, and battery fires is just one of the three of the many that I can think of. And this would continue making combustion scientists help a better world. Thank you very much.
Thank you, Guillermo, for your fantastic talk, for covering three very important topics. And we already have the three questions, but we only have the 5 minutes for the question for the answer. So one of them, let me talk to you. Some people saying the wildfire are carbon natural because they burn biomass fuel after all. Do you think this is correct?
That's a fantastic question. Thank you for that. So some wildfires can be carbon neutral. Some wildfires are carbon positive. And the key difference between them is when a fire burns, it has released carbon that had been captured by nature. And when it burns, it leaves a space in the forest for new fuel to grow. And this is what people say, well, if you burn a tree or a forest and it's replaced by exactly the same forest, then the cycle has become neutral. That is true if it happens within 7 to 10 years, because after 7 to 10 years, the carbon that has been released in the atmosphere has already affected the climate, and there is no way back, and it's irreversible. So a wildfire that takes place and the fuel that is burning is young fuel that will grow back again in 10 years, carbon neutral. If the fuel that is burning is ancient forest, we're talking about 100 years to 1,000 years. Well, not 1,000 years, not in a tree though. I'll tell you that now. Then the process is not carbon neutral, it's carbon positive. And if what is burning is the soil, I'm an expert in the burning of peat, for example. Peat is soil that is in the soil. It's carbon that is in the soil. It is actually 1,000 to 10,000 years old. It's very, very old carbon. When it burns, it's never carbon neutral. It's a net emission because the fuel will take way more than 10 years to grow again.
Thank you. That's the very perfect answer for that. Next question is, we only have 3 minutes left, so maybe this might be the last. Because the fire research tends to be considered very complex as compared to the other combustion researches. So do you have any suggestion on how next generation combustion scientists may better contribute to this dynamics and a complex field?
Yeah, that's a great question. And I try to answer also to that question in the talk today. What I see the future of combustion science is that we will be much more multidisciplinary, in the sense that we will be talking to ourselves, like in this community, obviously, and this symposium, but we'll also be talking to other communities, in the sense that we will not be solving only the specific problems that we've been dealing for the previous 10 years. Will we also be contributing our knowledge to the problems that other disciplines are dealing with? And the examples that I mentioned today, the three of them are topics that should be 100% within combustion science. But as you see right now, most of them are not yet. So there are thousands of scientists looking into wildfires. A small fraction, a really small fraction, are combustion experts. Battery fires, we're talking about billions of money involved into this topic. Very few of these millions pass through the hands of combustion experts. The burning of wood could be something that we can claim that is about half of it is in the hands of combustion experts, and that's good, but we still have more things to grow and to contribute to.
Okay, so you strongly saying that there's plenty of the room to be involved.
And I'm bringing the specific bias of what I know, right? Obviously. So I'm talking about fire safety, fire research. I'm sure that other people in different topics can see other venues of this crossroad to grow. But what I think it is essential is that we need to bring more combustion topics into the combustion community. And we should remain working on the topics we've been working on for the last many years. But we need to bring the new multidisciplinary dimensions of it.
Okay, thank you very much. So one another very quick question, please. There is a effective method to protect the wood material.
Sorry, a method to protect what?
Well, there is the effective method to protect the fire for the wood material, which is the timber.
Oh, well, yes. There are many different ways that wood can be protected, definitely, and all of them are being, as we speak, studied. The problem is that they already want to build these things. We cannot say that we need 10 years to study the details the things in detail. So it is. There are many venues I am actually familiar with at least 3 or 4 ways that this can be done. The question is that we have to convince the authorities, not just a few people. It's not just convincing my friends and my collaborators. I have to convince a lot of people that are involved in this.
Okay, thank you. All right, so time is unfortunately up. So let me move to the ceremony for the speaker of international keynote lecture. So let me pass the mic to the Dr. Fujimori, President of the Combustion Society of Japan.
Okay. Thank you very much for Professor Guillermo. It's a very nice talk and very suggestive for us. And actually, in Japan, we have only wood building 100 years ago. So you are talking about tall timber. It's very, very interesting for me, personally. Okay. This is a certificate of appreciation and from Combustion Society Japan, presented to Professor Guillermo Rein. With sincerity thanks for your outstanding invited lecture, Wildfire, Tall Timber, and Battery Fires, and the commercial science at the Crossroads with climate change and safety. At the 59th Symposium Japanese on Combustion, Gifu, Japan, November 22nd, 2021. Toshiro Fujimori, President of Combustion Society of Japan. Congratulations, Professor.
Thank you. Thank you so much. This is an honor for me. Thank you so much.
All right. Thank you very much, Professor Guillermo Rein again. I'm sorry for wake you up very early morning from the London. I'm hopefully you have the good day now.
Okay.
All right, so I appreciate it. Now I would like to close this session. Thank you for your participation and a great appreciation for the excellent speaker, Guillermo Rein. Thank you very much. ではこれでセッションクローズさせていただきたいと思います。
はい、中村先生、レイン先生ありがとうございました。これで、国際基調講演を終わらせていただきます。